Running a large language model entirely on your own laptop is the ultimate goal. It offers absolute privacy, zero API costs, and total offline freedom. But loading a truly capable model onto standard consumer hardware usually leads to a brutal physical bottleneck. On a traditional PC, the processor and the graphics card sit in separate memory pools. To generate a single word, the system must constantly copy massive blocks of data across a narrow physical bridge called the PCIe bus. This creates a persistent data jam known as the memory tax, which forces users to make compromises that often make the AI unusable. The first trade-off is speed versus logic. To make a model small enough to fit through that narrow pipeline, developers use quantization to compress the data. If the compression is too aggressive, the model's reasoning degrades. The second trade-off involves the context window. Users want to provide the AI with massive amounts of data, like entire code repositories. But as the conversation history grows, it consumes the available RAM. When that RAM fills up, standard AI runners dump the entire conversation history from memory. This forces the computer to painstakingly recalculate the entire prompt from the beginning before it can generate a single new token. Most portable hardware lacks the architecture required to deliver high-level intelligence and long context windows without sacrificing speed. Apple Silicon addresses this by placing the CPU and GPU in a single unified memory pool. By using zero-copy arrays, the graphics cores can access model weights instantly, removing the transfer delays found in traditional PC setups. This modeling overview shows that hardware bandwidth is only half the solution. Fitting a 3 billion parameter model on a mobile device requires a specific software engineering pipeline. Instead of compressing a model after it's finished, Apple uses Quantization-aware training to maintain accuracy even at a strict 2-bit weight limit. This data compares the Apple on-device model against competitors like Qwen and Gemma. The results show that the training pipeline produces a model that is small enough for mobile hardware while maintaining higher win rates in text evaluation than many larger open models. By integrating hardware architecture with specialized training, engineers have enabled high-quality AI performance on devices that fit in a pocket. Even with those optimizations, power users running massive 35 billion parameter models for complex coding will eventually hit a memory limit. The oMLX framework uses tiered KV caching to separate active context and cold historical data. When RAM fills up, older data moves to the max SSD, freeing memory for new computations. When needed, the model retrieves this context. Reaching 89% cache efficiency, this prevents recomputing the entire prompt history. By treating the AI's memory pool like a modern operating system handles virtual storage, developers have bypassed the rigid memory limits that once made massive models impossible on portable hardware. These two breakthroughs work in tandem. Advanced compression shrinks the model's footprint, while tiered caching extends its usable memory far beyond the physical RAM. This shifts the AI landscape. It demonstrates that high-level intelligence no longer requires a constant connection to massive, expensive cloud GPU clusters. This architectural shift allows a standard consumer laptop to function as a private AI workstation, capable of processing millions of tokens without a server connection. The development of local AI is moving beyond simple parameter counts. By focusing on memory efficiency, developers are creating powerful, multimodal tools that run entirely on the hardware you already own.